All right. Go ahead and respond to the online poll. Let me know that you guys are here. Let me we'll throw this in the corner. Okay. So today we will continue kind of in the other topics. So far we've covered kind of floating point numbers, and we learned about how the computer stores values that seem like real numbers, but they are just they are floating point numbers, meaning that there's only a finite number of them on the number line. And at a certain point, the computer's unable to distinguish between two different values because there's not enough bits to kind of keep track of that kind of last decimal place. So anyway, that's important to learn, to kind of just be aware of how the computer handles numbers. And now that we have that in mind, we can start talking about numeric methods, okay? And so, hang on, something's wrong with my pen. Okay, so numeric methods are a kind of a class of algorithms and programs that we can use to solve for to get, I guess, estimates of values that would otherwise require some algebraic work. Okay, so numeric methods, these are basically kind of little iterative algorithms. So these are just iterative kind of algorithms or instructions that help us estimate I guess I'll just say help us estimate certain values. Okay. To normally solve for these values, we would need to do algebra or calculus or some kind of something, but numeric methods will give us, pretty good estimates. Okay, so kind of, traditional methods require algebra or calculus. Okay, numeric methods just use the computer's ability to follow instructions very quickly in this iterative fashion to give us basically the same answer, okay, or a very high quality estimate of the same answer. Follow instructions quickly. Okay, so kind of our, and this, by being able to do this, we can then employ the computer to do much more complicated tasks, right? So, because the computer does not understand algebra, right? So somewhere in your mathematical training, you learn this concept of, here's this, we're going to use x to represent a missing number, and we can, put it in some kind of equation, and these two things are balanced, and we can move terms around following these mathematical rules, and we can solve for x, and things like that, okay? The computer, it's just storing numbers, and it has a few operations. It can combine numbers and add them together. you can multiply numbers, and you can divide numbers, and you can do stuff like that, but it doesn't have this right now, or at least at this level, it doesn't have this complex understanding of kind of this symbolic logic, okay? And so if we want to solve an algebraic equation, we can do it with the computer, but we're going to have to use a numeric method, and we have to frame our problem to be set up to employ a numeric method. So that requires a little bit of thinking on our part, but it will allow us to get some of these answers, okay? And so, our first class of numeric methods is going to be root finding methods, okay? So let me just see. A numeric method will take advantage of a computer's ability to follow instructions quickly. Keep in mind, a computer does not understand algebra or calculus. Okay. I mean, Wolfram Alpha and, Mathematica that is an attempt to try to get the computer to kind of, it's a whole language set up to get the computer to work in these mathematical terms, but your traditional programming languages don't employ stuff like that, okay? So anyway, first class of methods will be root finding methods. Okay, and so here, the idea here is we have some function x, and some function f of x, all right, and a root of f of x is the value of x where f of x equals 0, okay? So it's basically, where does this function cross the x-axis, at what locations, okay? So basically, where the function crosses the x-axis. Okay, and so, with algebra, all we do is we set f of x equal to 0, we do some algebraic manipulation, we solve for x, okay? The numeric method says, all right, here are some instructions for us to kind of get an estimate of what we're looking for, okay? So, numeric method will avoid doing math. I mean, like algebra or something like that to solve f of x equals 0. Okay, and so the first is sometimes, okay, so the first algorithm is going to be called fixed point iteration. Okay, some functions have something called a fixed point. Okay, so a function have a fixed point, okay, or fixed points. And so if we have some function g of x, I'll say a fixed point of g of x is where g of x equals x. Okay, let me go back to here. So root, if this is this, then this is a root, this is a root, and this is a root, okay? All right. Over here, a fixed point is maybe you've got some function like this, and the fixed point is right here. So if this is y equals x and this is g of x, okay, this is where g of x is equal to x, all right? So at this location, okay, and that's called a fixed point, all right? And we can sometimes these fixed points are we might call attractive, all right? In that, I don't know if that's a fire alarm. We're gonna have to evacuate. I'm like really nervous. Well, all right, we'll see. Because the alarms are like crazy loud, right? Okay, we're gonna go on. Hope it's okay. All right, all right. So what we can do is we can take advantage of what we might call attractive fixed points, okay? So, so for example, if you have the like the square root function has an attractive fixed point. Oh, it was my phone, or someone else's phone, and my phone just got the alert. Okay. The square root function, so here's an example. Okay, the square root function has an attractive fixed point. Okay, which means no matter what number you start with, if you take the square root of a function, or a square root of a value, you'll get another value. And if you take the square root of that value, you'll get another value. And if you take the square root of that value, you'll get another value. And if you keep doing this forever, where will you end up? Close to 1. No matter what number you start with, if you keep taking the square root, you will end up near the value 1. Let me find my calculator. So I think I can just demo this. So if I start off at 124, and then I take the square root, I get 11.113. Square root of that is 3.33699. Square root of that is 1.8267. Square root of that is 1.35. Square root of that is 1.16. 1.078. Square root 1.02. And I keep doing this, and we get closer and closer and closer and closer and closer to 1. Okay? I could start off, well, okay, no negative numbers, but 0.000047, okay? I take the square root of that and I get this, and it keeps climbing until we get to something. Now we're at like 0.99999999999, okay? And no matter what number we plug in, okay, if I take the square root, just after a few iterations, we're down to something pretty close to 1, okay? And so that's an example of a function with an attractive fixed point, okay? And a lot of functions have attractive fixed points. Not all of them, but a lot of them do, okay? Which means if we can rewrite our original root finding problem into a function with an attractive fixed point, all we have to do is just iteratively apply that function, and it will focus in on the fixed point And if we've reframed our problem in such a way that that fixed point is equal to the root, then we're in good shape. Okay, let me write this down. All right, so the square root function has an attractive fixed point, and what that means is if we iteratively apply the function over and over, fixed point, I'll say at x equals 1, over and over and over, okay, no matter what value I start with, it will converge to x equals 1, okay? Because the square root of x is equal, square root of 1 is equal to 1, so 1 is a fixed point of the square root of x. So here's our strategy. Okay. We have a function f of x. We want the roots. We want roots of f of x, okay? We rewrite f of x equal to 0 into the form g of x equal to x, okay? So we rewrite f of x equal to 0 into the form g of x equal to x, okay? If we can find the fixed point of g of x, okay, we have solved for a root of f of x. Okay. The tricky part is there's often many ways to get to rewrite g of x equal to x. Okay, there's many ways to rewrite f of x equal to 0 into this form, and only some of them will have attractive fixed points. Okay, so maybe the challenge is there are often many ways to rewrite f of x equals 0 into g of x equal to x, and only some of them have attractive fixed points. All right, so here's an example, okay? So this is an example from textbook. This is Spurs chapter 10. So we've got f of x equal to log of x minus e to the negative x, okay? And we want to solve for roots, so we're going to set it equal to 0, okay? We want the roots of f of x. Okay, so for option 1, I will rewrite log of x minus e to the negative x equal to 0. I'm going to just do some manipulation. Log of x is equal to e to the negative x. I move it around, and then I raise e to exponentiate both sides. E raised to this side and e raised to this side, okay? And so now I get x is equal to e raised to the e to the negative x, okay? And then so what we'll do is we will let g of x be equal to, I'm going to just rewrite this as exp of exp of negative x, and we set that equal to x, and we'll try to solve for x, okay, a fixed point of g. Okay, so that's one way to do it, okay? And so to run the algorithm, okay, this is what we would do. To run the, I guess, fixed point iteration algorithm, we start at an arbitrary value of x. We'll call it called x0. And then what all we're going to do is we find g of x, g of x0, okay, and use that as our next value, x at time 1, okay, and repeat, which basically says x at the next iteration is going to be equal to g of x at the current iteration. Okay, and that's the entire algorithm, fixed point iteration, okay? xn plus 1 is x at the next iteration, and xn is x at the current iteration. Okay, so we can just try this, see if this works. So here, what I have is g is equal to exp of negative x, okay? Let's see, sorry. Working on some stuff here. Okay, so R has the exp function. So if I can do exp of 1 is e raised to the first power, exp of 2 is, that squared. Okay, so anyway, I'm going to just say g is a function of x, and what will it return? It will return exp of negative x. Okay. And so I can just start off with, I'll say x equals 10, or just some arbitrary value, right? X equals 10. And then what I'm going to do is I'm going to just do x is equal to g of x. All right? So I'll say x is that. And then maybe just so we can see what it did, is we'll plug it in there, okay? And we'll just repeat over and over, whoops, okay? And I just iterate, and okay, and it seems like it's converging on some value here, okay? So it looks like we're kind of stuck at 1.3098, okay? Something around there. So we started off with 10, and then it went down to 1.00. Then we plugged that in and went to 1.44. We plugged that in and it gave me 1.26. We plugged that in and gave me 1.33. And then now we're kind of stuck at 1.3098. Okay, so this is kind of, it seems like we've converged to something around 1.3098. Okay, and we can check to see, is this indeed a root of our original question, f of x. Okay, so f of x is log of x minus e to the negative x. Okay, so we can say, all right, so what is x? X is currently 1.3098, and we can say, okay, well, what is log of x minus e to the negative x, right? All right, and we can ask, what is that? And it gives me something that's pretty close to 0. So indeed, using this simple fixed point iteration algorithm, we've found a root of this original function. Okay. Is that okay? But again, the problem is not all functions will have an attractive fixed point. Okay. So if we tried something else, okay. So I don't know. And so, you know, here what you'd probably want to do is you'd probably want to write a, here I just kind of manually did it and we were just kind of eyeballing to see when it stopped, right? But probably, you know, if we wanted to write some pseudocode here, okay, so what you'd have is you would probably need while, and you would have kind of the absolute value of x old minus x new, okay? Kind of the difference between your last iteration and your current iteration, while that is above some tolerance level, okay? Then all you're gonna do is you're gonna take the current value and make that the old one, and then replace the new value with g of the last value, okay? All right, and that's basically it, right? So this is just kind of the algorithm. All we're doing is we're just taking the x, applying g to it, and this, okay? All right, but warning, not all functions have attractive fixed points. Okay, so if you the rule is if the slope is less than 1 at a fixed point, the fixed point is attractive. Okay. Otherwise, it will diverge. All right. Okay. Is that okay? I'll kind of, let me see if I can screenshot this. Here, I'll go ahead and I'll write, I don't know what just happened there. I'll go ahead and I'll write our little code. So I'll just do while absolute value of x old minus x new is greater than some tolerance, then we'll just write x start there. So I'll say x old is equal to 10 and x new will be equal to g of x old. We'll apply that. And I don't know, my tolerance will be equal to 1e minus 6, okay? Okay, so it's done, and we can ask, okay, what is our current value of x new? That gives me that. If I plug that in, we get something, you know, pretty close to 0. Okay. All right. So there's your code. Throw that in the notes. Okay. So that's what's going on. I'll have you guys implement this in your homework, and you'll draw some graphs to kind of visualize how this thing's coming. So new homework assignments coming. I know you guys are excited. All right. Okay. We'll probably have time to cover maybe one more, and we'll have to cover some more later. Okay. We have Newton-Raphson method. Okay. So this is another root finding method. Okay, Newton-Raphson method for finding roots. Okay, and the way the Newton-Raphson method works, so I'll just draw this. Okay, and is there am I able to draw curved lines? No. Okay, well, maybe. All right, so imagine this is a smooth line here, okay? And so the way it works is you're going to you start at arbitrary x0. So that's your first iteration. Okay, so let's say I start right here. And then you will you'll find, so visually this is how it works, okay? You're going to find f of x0. Okay, so this is, here's our function f of x, and this is the root, right? And this is the root that we want. Okay, you find f of x, and then what you're going to do is you're going to draw a tangent line from f of x. That's not quite tangent. It's quite hard drawing on this thing. Okay, all right. My life is so hard. Okay, all right, I don't know what I'm doing. All right, I'm gonna just have to freehand draw a line. This is, okay. All right, so we're gonna pretend that this is tangent. All right, I know it doesn't look that way, but we're gonna pretend that this is tangent, okay? And we draw the tangent line. Draw a tangent line from the point x0 and f of x0 to the x-axis. Okay, and where it hits here, this is going to be the next value we repeat. Okay, so where the tangent line crosses, tangent line crosses the axis, that will be x1, okay? And then we repeat. Okay, so this is our first iteration. The next iteration, we start here, and we go up to, this is going to be f of x1. I draw a tangent line here. Okay, and this will become x2. And then I repeat, this is f of x2, and I draw a tangent line here, okay? And we get closer and closer and closer to the root, so on and so forth. Does that kind of make sense, what's happening? Okay, and that is the Newton-Raphson method. Now, how can we come up with a simple equation for finding x1, or the next iteration, okay? So let's take a closer look at what this looks like, okay? So this will be, so basically what I need to know, all right, I have my rise, and basically what I need to know is my run over here, right? I've got rise and I've got run, and so basically, so far we can say the next iteration is going to be equal to the current value minus the length of the run. Okay? So what is going to be the length of the run? Okay. Well, what do we know? We know a few things, right? We know we can get, so let's take a look at our triangle here. So here's xn, and here's going to be xn plus 1. And I've got the rise. Here's the run. We want to solve for the run, and I've got f of xn, right? So my rise is equal to f of xn minus 0, okay? So my rise is equal to f of xn, okay? And what is my slope equal to?
Prime.
Yeah, slope is rise over run, and this is equal to f prime of xn, right? So if I know the slope, I can solve for the run by saying run is equal to rise divided by the slope. Is that okay? So my slope is equal to rise over run. So if I just solve for what the run is, then this will give me the rise, which I know to be f of xn, and I divide by the slope, f prime of xn. Is that okay? So, so the algorithm boils down to the next iteration, xn plus 1, is going to be equal to our current value minus whatever the run was, which is f of xn divided by f prime of xn. So this is a NewtonRaphson algorithm. Okay, and so this requires for us to know what f prime is. Okay, it requires that we have a function for f prime of x. Okay, is that all right? Okay, so let me just do a very silly example, okay? Simple example. All right, let's say f of x is equal to x squared minus 4. So we've got a parabola that dips down, and so we have a roots at x equals 2 and x equal to negative 2, okay? So right here, I'm going to create a function. I'm going to just go ahead and do this in R. I think I got to make my screen a little bit bigger for you guys. Okay, what I'm going to do is, so we have f of x equal to x squared minus 4, all right? So what I'm going to do is I'm going to make a function of x, and the function will return both the value f of x and f prime of x. Okay, so f of x, which I'll call fx, this is going to be x squared minus 4. Okay, and f prime, what's the derivative of x squared minus 4? 2x, right? Okay, so not too hard. And then what we're going to return is you can only return one object, so we're going to just combine f of x and f prime. All right, and that's what we've got. All right, so this is going to be my function here. Let's actually clear everything out. Okay, and so we can just kind of see, all right, what is f of 5? Okay, f of 5 says it's 21, and the derivative at f of 5 is 10. Okay, and this, and then I can get the actual value. I can just say, you know, f of 5 bracket 1 will give me the value, and f of 5 bracket 2 will give me the slope. Okay, so to access the value, okay, and so NewtonRaphson basically will be while what? We're gonna kind of, it's just gonna keep iterating, so we're gonna say the absolute value of x new minus x old, while that's still greater than some tolerance level, what are we gonna do? We're gonna say, we're gonna take our current value, which is x new, and store that as our old value, and then x new is going to be what? It's going to be x old minus the value f of x old, f of x old divided by f of x old, the slope. So we take the current value minus the value divided by the slope. So it's just an implementation of exactly this. We're saying our current value xn minus f of xn divided by f prime of xn, which is what I've got here. Is that okay? So we're gonna let that run. So again, probably I'll have to just say x old is gonna be equal to, I don't know, 10 or something. And then we'll start off here. And then I'll say tolerance is equal to 1e minus 7 or something. All right, just some 1/1,000,000th of a value. All right, we'll let that run. Okay, it's done. And what is our x new value? X new is 2. The value, yeah, it's pretty close to, it's pretty small. Okay, so this is where we are ending up. Okay. And so even though I started off at 10, it worked. I can try out negative 10, okay? Does it work on the other side? Okay, and we can see kind of x new is negative 2, okay? So one thing about NewtonRaphson is it's gonna find a root, but depending on where you start, it might find different roots, okay? And you don't really know which root you're gonna get, okay? So anyway, so I'll copy my my code here. That's no good. Okay. I guess. All right. So I'll just write NewtonRaphson may find different roots depending on the starting point. Okay. Also, if also sometimes, okay, all right. let me just note one thing, okay? Other weird issues, okay? If for some reason you end up, like your function has something like this, okay? And in the course of, it will fail if f prime of your current iteration is 0. So if it ends up here, it's gonna fail, right? So because the tangent line is parallel, okay? And if it's just off, okay, and it will can cause problems if f prime of xn is not 0 but close to 0, okay? So you might have something that's not exactly parallel, but you might have something that just the tangent line ends up being like way out there, and it doesn't cross until over here, okay? So here, if the slope is 0, it's going to be parallel and it'll fail. And if the slope is just very close to 0, you might suddenly, the run is going to be like 1,000,000, okay? And you can end up like, I don't know, who knows where, okay? And that can cause issues. And sometimes you can end up in a loop where, just depending on your starting point, you keep ending up where you started over here and then you end up over here, but then this tangent line sends you back to where you started from, okay? And that's possible, okay? You can also get stuck in these loops. Anyway, okay, so that's NewtonRaphson. We'll take a look at a couple other root finding methods on Friday, okay? All right, so we'll see you then.